Welcome back to the course entitled Chemical Crystallography. This is the 12th week of this course, and by now you must have learned a lot about this subject and also learned about how to collect X-ray diffraction data, solve and define the structure and so on. And in the previous weeks we have demonstrated how one can use a powder and a single crystal diffractometer. So today in this lecture I am going to discuss about the method which is called device error method of unit cell determination, identification and indexing of cubic crystals. You know that X-ray diffraction methodologies are nearly 100 years or more than 100 years old, and in the very beginning, in the very initial days of powder X-ray diffraction, the diffraction data used to be collected using X-ray films, and those films used to be exposed with the crystal in the middle, and the diffracted beam would generate white lines on the film, and based on the location of those white lines, Peter Debye and Paul Scherrer developed a method of indexing of crystals, mostly the cubic crystal systems. So on modern days diffractometer, what we get in a powder diffractometer, what we get is the intensity versus diffraction angle 2 theta, and using the values where the peaks appear, one can identify the values of HKLs that you see in this figure given above. So what we do is we try to find out these 2 theta positions, and we use Bragg's law to compute the corresponding d values using n lambda equal to 2d sine theta, and then we have introduced you to the relationship between theta and HKL in one of our previous lectures. So that particular expression, which comes directly from Bragg's law, can be modified to this equation, which is sin square theta equal to lambda square into h square plus k square plus l square by 4a square for a cubic system. So using this equation one can find out the value of A and HKL very easily. Let us see this with one example. Suppose in a given diffraction pattern you are getting a series of 2 theta values as shown here. So as per the previous slide's expression, we need to calculate the sin square theta value for all of these reflections. So we try to note down these numbers, the sin square theta values, up to about 5 decimal places, and then we play a trick. We divide all these numbers by the first number always. That means sin square theta 1 is divided by sin square theta 1, sin square theta 2 is divided by sin square theta 1, sin square theta 3 is divided by sin square theta 1, and so on, and we generate these numbers. Now we keep these numbers approximate up to second decimal place and try to look at it, seeing that whether it comes close to any integer value. So when we do that, we see that these are not integers. So then we try to multiply it by 2 or 3 or 4 as the case may be to convert it into nearest integral values. So then by multiplying these numbers by 2, you get 2, 3.03, 4.12, 5.07, 6.10 and so on. So these numbers then can be approximated to the next integer values, and we end up getting numbers like 2, 3, 4, 5, 6, 8, 9, 10, 11 and 12. So these numbers or these integers represent the sum of squares of 3 numbers. So now we need to guess what could be the values of h, k and l. So when it is h square plus k square plus l square, the only possibility is 110 or 010 or 011. That means 2 of them is 1 and the last one is 0. When it is 3, all 3 of them are 1. So that is 1 square plus 1 square plus 1 square. For 4, it is 2, 0, 0. For 5, it is 2, 1, 0. 6, it becomes 2, 1, 1. That is 2 square is 6. Remember that this 2, 1, 1, when I am writing, I am actually indicating that the family of plane 2, 1, 1. That means it can be 1, 2, 1, it can be 1, 1, 2, or it can be 2, 1, 1. So like that, I can compute these numbers H, K and L for all the reflections. So now when we know H, K and L, we know the corresponding D values. You can calculate the A value, right? We get to know the D values from 2 theta values using n lambda equal to 2 d sin theta. So you calculate the D values and we use the formula, that is A equal to DHKL into square root of H square plus K square plus L square. So for every individual reflection you can calculate the value of A, and what you see is that the value changes slightly from top to bottom. So one has to take the average of these numbers and give this number as the A average, which is the unit cell parameter of this particular crystal, that is 15.4540 angstrom. You remember this sequence of numbers, this 2, 3, 4, 5, 6, 8, 9, 10, 11 and 12. Now let us go to the example 2. We do it again in the similar manner. We calculate sin square theta. We calculate sin square theta n by theta 1. And then we see that we need to multiply here by 3. Then only these numbers, which are sin square theta n by sin square theta 1, can be converted to nearest integers. So then these numbers can be, when we convert it into integers, they turn out to be like this: 3, 4, 8, 11, 12, 16, 19, 20 and so on. So then again we try to guess what should be the H, K and L, such that there are sums of the squares of those numbers will be 3, 4, 8, 11, etc. You see, when we want to go 11, it is 3, 1, 1, but it can be 1, 3, 1 or 1, 1, 3 and so on. So these numbers, these HKLs indicate the corresponding family of planes. Now we have a third example here. We do it in the same manner. Sin square thetas are calculated. Then you convert it to sin square theta n by sin square theta 1. And you see here now these numbers itself are very, very close to the corresponding integers. So we can straight away convert them into the corresponding integral values. And then we notice that there is an integer 7. Now what we see is 1, 2, 3, 4, 5, 6 can be represented as sum of squares of 3 integers, but 7 is such a number which cannot be represented as a sum of square of 3 numbers. So because of that number 7, this series of numbers is not acceptable set of numbers for h square plus k square plus l square. So at this point here we need to multiply this by 2 to get this set of numbers. So 7 becomes 14, and then this series of numbers now can be converted to HKLs logically, with HK and L being integers. So these integers then represent the corresponding indexing of those reflections. So the planes appearing at different 2 theta values will have these HKL values as indexing. So we see there are different types of sets of numbers for h square plus k square plus l square. So when this series of numbers like 2, 4, 6, 8, 10, 12, 14 and 16, this represents a BCC system. This represents, if you look at the corresponding HKL values, this represents the systematic absence that is observed for a body-centered cubic system, and hence series of these numbers for h square plus k square plus l square represents a body-centered system. The one which we got in the previous case, that 3, 4, 8, 11, 12 and 16 represents a face-centered cubic. Which we did not encounter is something called like simple cubic, where these numbers will be 1, 2, 3, 4, 5, 6, 8 and 9 and so on, and that will correspond to a simple cubic system. So this indicates very easily one can identify the lattice type, whether it is simple cubic, body-centered cubic or face-centered cubic, and one can easily calculate the corresponding 2 theta value, one can calculate the A0 value very easily using any one of those reflections, but it is better that we calculate the A values for all the reflections and take the average of A values as the correct A value for that particular unit cell. So with this, I would conclude this lecture, and I would ask you to follow this type of examples that are available in several textbooks, and you try to do your calculations, you try to estimate the cell parameters of those given problems. So we will meet you in the next class discussing about another different methodology. Thank you.